have a positive relationship between x and y. And in the same way, when x increases and y decreases, we call it a negative relationship. So we're gonna take a lot of observations, and we're gonna try to find the line that is gonna fit. And this line has to be the closest to each observation. And this is called regression line. So what we are trying to do is to minimize errors. So we have the x variable and the y variable and many observations. Supposing we have this line that's going to fit, we are trying to minimize these distances between the line and each observation. In the way that if we sum all of these distances, we're going to find the minimum of the sum. So we are going to minimize our errors. Let me give you an example of a positive relationship. Study time and grades. When study time increases, grades increases. Another example, which is going to make the relation between the estimated value and the study time, which is the independent value. So we have y hat equals BO plus B1 squares x, where x is the study time. What we're trying to do is to find the BO and B1 that are going to make our line fit, which means the best BO, which is the y-intercept, and B1, which is the slope, in the way that we're going to find the best line to predict other values of y. Another relationship, negative relationship in this side. When time on Facebook increases, grades decreases. So this is a negative relationship. In this case, we're going to find another relation in the equation. So the estimated value is going to be BO minus B1 squares x, where BO is the same y-intercept, and minus BO, which is going to be negative in this side, is the slope. So to find the best BO and B1, we can use either the cost function, right here, or the graded distance. But in practice, we are using the least squares. So how can we find BO and B1 from the least square? We have here some values of x and y. We're going to find the mean, which is 3 for the x variable and 4 for the y variable. We're going to drop the mean lines, and what we're going to try to do is to calculate the distance between the line and each observation. So every single line have to pass by this point, which is 3 and 4. 3 is the mean of the independent variable, and 4 is the mean of the dependent variable. We are going to calculate the distances between the x mean and the observations, and then do the same for the y means. We're going to find these results, so negative 2, negative 1, 0, 1, 2, and negative 2, 0, 1, 0, 1. What we're going to do with these values is calculate the square of the distance between the mean line and the observations, and we're going to find these results and then multiply this column by this column. And this to find the value of B1. And B1 is going to be the sum of the multiplication of this column by this column on the sum of the squares of the mean of the distances between the mean, the x mean, and the observations. And once we find the B1, we're going to find the BO. And this by, so we have here the predicted value of y equals B1 found, which is going to be 0.6 plus B1 multiplies x. So we're going to simply take a point, the intersection, for example, and find we give any value to x, we can find an estimated value of y, which is y hat. So we have seen the linear regression. Now we're going to explain another type of regression, which is logistic regression. So logistic regression is another technique borrowed by machine learning in the field of statistics. It's the go-to method for binary classification problems, such as spam and not spam emails. So the logistic regression is similar to linear regression, except that for logistic regression, it predicts if something is true or false instead of predicting a continuous value, like weight or range or length. And another difference between logistic regression and linear regression is that in linear regression we are trying to fit a line, whereas in logistic regression we are trying to fit in this shaped logic function where the curve goes from O to 1, which means that this curve is going to give you the probability that the mouse is obese. For example, if we take a pretty heavy mouse, the probability of being obese is pretty much high. And if we take an intermediate mouse, there is only 50% probability that this mouse is going to be obese. And if we take a small mouse, there is actually a small probability that this mouse is going to be obese. Another exception is that the logistic regression is usually used for classification. For example, if the probability of a mouse being obese is bigger than 50%, so it's going to be classified as obese mouse, and otherwise it's going to be classified as not obese. So another big difference between linear regression and logistic regression is that in linear regression we use the least squares method. So in logistic regression we can't use this method, but there's something called maximum likelihood. So we are just going to take a probability like this curve, and then we're gonna calculate the likelihood of this mouse being not obese, and do the same for the other mouse, and do the same for all the mice, and we're gonna multiply these likelihoods together, and this is gonna be the likelihood of this curve. So we're gonna shift the curve and do the same, calculate the likelihoods, and multiply all the likelihoods together and find out the second likelihood. And do it a lot of times, and the best curve is gonna be the one with the maximum likelihood. So I don't want to confuse you, but the likelihood, we calculate the likelihood of each observation using a logit function. So a logit function is log p of 1 minus p. And using this formula, we're going to find another line, logarithmic 1, and from this line, for example, this, and from this line, we're going to find each likelihood for each observation and multiply all the things together to find the maximum likelihood. So now we're going to move on to another basic algorithm, which is decision tree, and my friend JORFI Khalil is going to explain it to you.
Good morning. I'm going to try to explain one of the most used methods in machine learning, and I'm going to try to simplify each method with real life business examples. And I'm going to try to avoid the mathematical properties so I don't confuse you. First of all, we've got the decision tree. So it's a type of supervised machine learning where the data is continuously split according to a certain parameter, like a tree. For example, in this example, the first parameter is whether or not the person is under the age of 30. Second of all, the tree can be explained by two entities, namely decision nodes and leaves. The leaves are the decisions of the final outcomes, like fit or unfit. are the leaves, and the decision nodes are where the data is placed. Like it's a lot of pizza is a decision node. Exercises in the morning also is a decision node. So we're gonna try, like I said, I'm gonna avoid mathematical technicalities. I'm gonna explain to you decision tree with a more complex example. Let's say you wanna